Hi there, and thank you so much for joining me. This is the third video in our Module 8 series, and Module 8 is providing an introduction to statistics. So in this particular video, I am going to talk about measures of central tendency. So another word for measures of central tendency is average, right? So what does average mean? So I mentioned that with descriptive statistics, our objective is going to be to describe or explain and organize our data set or distribution, right? So because we're trying to describe all of the data in our distribution or the data that we've collected from our sample, okay, one of the best ways to do that is to calculate a single value that summarizes the entire distribution of scores, right? So remember in my first video, I talked about the example with the 50 exam scores, right? And so once we create something like a frequency table, right, we can start to see maybe the highest and lowest values. We can start to see the proportion of students that got a particular grade, right? And we start to get a sense of maybe what the most frequent score was. But the best way to get a sense of how students performed on that exam is to find a way to, in a single value, represent the whole distribution of scores, right? So our goal when we compute an average is to find one statistical value that best represents an entire group of scores. So this is what we call our measure of central tendency, right? So sometimes it's easy, right? We can look at our frequency table or our histogram and it becomes very, very obvious what the average is or the measure of central tendency is, right? Just looking at the graph automatically, you know, there's the tallest bar there on our histogram is for the score 7, right? So we would say that the average of that distribution of data is definitely 7. It jumps right out at us, right? Other times it becomes less clear, right? So it still looks like 7 is probably the most frequent score, right? But 8 is also very frequently, or excuse me, in this case, the tallest bar there is 8, a score of 8, but 7 is also a very frequent score there. So how do we know? Is it 8 or is it 7? Right? And then other times it makes no sense, right? So if we simply look at the frequency bars there, it seems like there are two averages. So the two averages we might assume from looking at this distribution are both 5 and 8, right? But how is that possible, right? So sometimes it's very clear, but oftentimes it is not. Okay, so fortunately, there are actually 3 different averages we can choose from, or measures of central tendency we can choose from, depending upon the nature of our data set or our distribution. So the one that you guys are probably most familiar with is the mean, right? And that's probably what you think of when you hear average, right? So the mean is just the average of all of the scores, right, that we calculate. So the formula for the mean, as you probably know, First, let's start with the M here, okay? So a capital M or X bar is going to indicate a sample mean, whereas population mean is typically written as the Greek letter mu, okay? And to calculate the mean, as represented here, we simply add up all of the individual scores, which are denoted by a letter X, right? So to get our mean, we add up all of the values of X and we divide it by the size of our sample or the number of values or observations that we have, right? So if we have 50 exam scores, we would divide our summed up individual scores by 50, okay? And the size of the sample or the number of data points that we have is represented as the letter N. Okay, so again, you guys have probably known this since elementary school, but I'll just give you an example problem, right? So if we're looking at our sample, which is comprised of customers at 3 different store locations, right? To calculate our sample mean, or M, we would simply add up 3,564 plus 1,534 plus 2,150 and divide by the number of values in our data set, which is 3, and we would get an arithmetic average of the mean, which is 2,416. Okay, so that's simple enough. So for example, let's say that we are interested in reporting the annual income of people in Macon, or we're attempting to find the average income of individuals living in Macon, right? So we collect a sample from 9 individuals who report their annual income, and these are the scores that we come up with, right? So we have 9 data points here, and they range from 28,000 all the way up to 260,000, right? If we were to report the mean of these values, okay, using the same formula that we just went over, the mean of these values is $62,000, okay? So based on all of the data points in our distribution, do you think it is misleading to say that the average person in Macon makes $62,000 a year, right? And remember, our goal in calculating an average is to find the best possible value to summarize all of the data points in our distribution, right? So do you think $62,000 a year is a value that does that, right? Probably not, because with this particular data set, there's one value that seems to be pulling the mean up, or increasing the mean, right? So obviously here that value is 260,000, right? That is clearly an extreme score or an outlier in our data set, right? It is much, much higher than most of the values in the data set. So what do we do when we know that the mean is not accurate as a result of an extreme score or outlier? Well, one option is to use, instead of the mean as our average, to use the median as our average. Okay, so let's suppose we took this data set and we found that the median of these values is 40,000. right? That's probably going to be a much better representation of our data set, right, than 62,000. Okay, so again, when the mean is influenced by extreme scores or outliers, the median may be a better representation of the average score. Now, in order to be as thorough as possible, it probably makes sense to report both the mean and the median, right? Just to be as thorough as possible. But it's clear that the median is probably a better estimate of the average in this case than the mean. Okay? So what is the median? The median is quite literally the middle score. Okay? So it's the middlemost value in our data set, such that half of the scores in our data set are higher and half of the scores in our data set are lower. Okay, so in our first example, we had 9 scores in our data set. Okay, so it was fairly easy to find the middlemost value, where 4 scores were less and 4 of the scores were greater, right? So in that case, the value would be $40,000, right? On the previous slide. Okay, so how do you find the median? You take all of the values in your data set and arrange them from the lowest possible value to the highest value. And then you choose the value, provided you have an odd number of scores, you choose the value at which there are the same number of scores below it as there are above it, right? But what do you do when you have an even number of values, right? Well, in that case, you do the same thing, okay? But you simply take the mean of the two middle values, right? So here we have 40 and 41,000, right? And below the 40,000, there are 1, 2, 3, 4 scores. And above the 41,000, there are 1, 2, 3, 4 scores, right? So that is clearly those two values are clearly our middlemost values. And we would simply calculate the mean for both of those values. So we have 40,000 plus 41,000, and then we divide the sum by 2, and we get 40,500 as our median. Okay, and we have one more option in terms of the kind of averages that we can compute, and that is the mode. Okay, so the mode is the score that occurs most frequently within a sample. And it's possible to have one mode, in which case your distribution would be unimodal, or more than one, okay? So for example, if you had 2 modes, your distribution would be bimodal. Okay? Modes are typically used only for categorical variables, right? But if your variable is continuous, you can report the values that occur most frequently. Okay, and for categorical variables, you would report the categories with the highest count, as well as the percentage of the sample that falls within those categories, right? So for example, if you had a distribution of exam scores that would be a continuous variable. Okay, so if you had, you know, 4 people score a 78 and 4 people score a 93, okay, and all of your other exam scores had frequencies between 1 and 3, okay, then you would say that your modes, your distribution is unimodal, and your modes are 78 and 93 respectively, right? That's for continuous variables. Let's say you have a categorical variable though. Okay, so let's say this is your distribution. Okay, so right away we can see that this distribution is categorical, okay, because there are different levels, and we can tell right away that it's bimodal because there are 2 modes, okay? So both, we have the same number of sophomores and juniors, and they have the highest frequency values, okay? So how would we report the mode for this, for this data set, okay? Well, first, we would want to add up all of the frequencies so that we know how big our sample is, right? So let's start with freshmen. We can see that we had 4 freshmen in the data set, and we had 10 sophomores and 10 juniors respectively, so that's 24. And then we had 6 seniors, right? So our total sample size for this distribution is 30, okay? So what we're going to do whenever we report categorical variables, okay, is we're going to report the categories with the highest counts or frequencies, as well as the percentage of the sample that falls into those categories, okay? So if we were to report the mode for this data set, we would say there are 2 modes. It's a bimodal distribution. 33.33% of the class are sophomores, and 33.33% of the class are juniors. Okay? So again, we add up the total frequency, we add up all the frequencies to get the sample size, and then we divide 10 by 30, and that's where we get our percentage from, okay? And again, for categorical variables, we are reporting the category along with the percentage, whereas with continuous variables, we're just reporting the continuous values that occur most frequently in our data set. Okay, so in sum, most of the time when you are calculating averages, you will use the mean, but you only use the mean when you have a continuous variable. Okay, when you have outliers or extreme scores in your data set, you should report the median in addition to the mean. Okay, and again, you only do that with continuous variables. Report both the median and the mean. And then for categorical variables, okay, you are going to report the mode. And you should also always remember that there can be more than one mode in a single distribution. Okay, so mean and median are for continuous variables, and the mode is for categorical variables. So I'll talk more about this in my future videos, but I wanted to at least introduce this idea here. So one of the most important assumptions that we can make, or that we do make in statistics, is that the variables that we are analyzing in our sample are normally distributed in the population, right? So in theory, if your sample is big enough, the distribution will look like this, okay? Where most people are clustered in the middle of the distribution, and there are only a few extreme scores, okay? And so essentially what I mean by normally distributed is if we were to take our data set and create a frequency graph, like a histogram, the histograms I showed you in my last video, okay? So we have our frequency histogram, okay? And then we draw a line, rather, to connect the tops of the bars in our histogram to create a smooth curve. Essentially, with a variable that's normally distributed, it's going to have a histogram that is bell-shaped, okay, with only one peak, and it's going to be symmetrical about the mean, right? So again, most of the variables or most of the data points are going to fall directly in that sort of meaty middle part of the curve. Okay. So what are some of the variables that are likely to be normally distributed? Well, there are a lot of characteristics of the population that fall within that normal curve or that bell curve shape. So for example, things like height and weight and IQ and often exam scores are going to approximate the normal curve, right? So again, one of the most important assumptions we can make in statistics is that our data set is normally distributed, or our variables are normally distributed in the population. Okay, so many statistical tests assume for continuous variables that they fall within a normal distribution. Okay, but fortunately there are also ways to check for normality, particularly if you're using SPSS, which is the program that you guys are learning to use. Okay, so again, this is a fundamental assumption in statistics, but there are things we can do if our data set doesn't conform to the normal distribution, which we'll talk about later. But for now, it's just important for you to know what I mean by normally distributed variables and maybe have some examples of the types of variables that are typically normally distributed in the population, right? So a normal distribution is going to have a histogram or a shape that is bell-shaped with only one peak, and it's going to be symmetrical about the mean. So as I mentioned in my previous slide, variables that approximate the bell curve or the normal curve are going to have a symmetrical shape, right? Where the values are, where there's only one peak that falls within the center of the distribution, right? So we can either describe distributions as symmetrical or approximating the normal curve, or skewed. And there are two types of skewness that we can talk about, or two types of skewed distributions that we can talk about. So a positively skewed distribution, by definition, is going to have more extreme values at the higher end of the distribution, right? So that means the tail of the distribution is going to fall on the right side of the curve. So what's an example of this that might be a little bit more pragmatic? Well, if we were to, again, assess income and collect a sample of annual incomes in Macon or wherever, a positively skewed distribution would be such that most regular people or average people are going to approximate that single peak, but there are also a few billionaires in our distribution, right? Which is going to, again, move that tail to the right towards the more positive values, right? In contrast, a negatively skewed distribution is going to have more outliers or extreme scores on the lower end, which is going to cause the tail of the distribution, which is where outliers are found, to move to the left where the smaller numbers are, right? So an example would be an easy test where most people do well, okay, but there are a few people who get very, very low scores, right? Because again, those outliers are going to cluster to the left where the lower exam values are, okay? So that is how we would describe the symmetry of a distribution. Again, with a normal curve, all of the values are going to be clustered about the middle, but with a skewed distribution, that tail is going to move such that we have more outliers either to the left or to the right. All right, so that concludes my lecture on measures of central tendency, and I will see you in my next video.